So our second speaker is Prasad Raghavendra. He's on the faculty at Berkeley, and previously he was at Georgia Tech. Prasad did his postdoc at Microsoft New England, and before that did his PhD from UW, advised by Venkat Guruswamy. So Prasad has done phenomenal amount of work in understanding hardness of combinatorial optimization problems. There was a time when people tried to get hardness results based on unique gains for every CSP. Prasad put them out of their misery and showed how a single semidefinite program gets the optimal hardness, the optimal algorithm for every CSP. Of late, then he has been trying to understand lower bounds on the size of semidefinite programs, how extended lower bounds on extended formulations. For his work, Prasad has gotten a number of honors, including the Sloan Research Fellowship and Career Award and multiple Stockwest Paper Awards. So we're delighted to have Prasad here. Thank you.
Thanks for the kind introduction. Thank you for the invitation. I've had a good time here. So, I'm going to talk about lower bounds on the size of semidefinite programs. This is joint work with James Lee at University of Washington and David Stoyer. So here's to set up the question, let's look at the following problem, which is fairly well known, which is a traveling salesman problem. You're given a graph and you want to find the shortest tour that visits every one of the nodes exactly once. And one can formulate this as a convex program in a natural way. So what do you do? Look at the set of solutions for this problem. Each solution is a tour, and then for every tour you encode it as a Boolean vector of n squared dimensions. So the ijth entry is 1 if you traverse the edge ij in the tour, and then you look at the convex hull of all these vectors. So this is a polytope, and the thing is, if you could optimize a linear function over this polytope, then you can exactly solve the traveling salesman problem. And since traveling salesman problem is NP hard, we don't expect this to be easy. In particular, it should be exponentially hard to optimize linear functions over this convex region. In fact, it is so. In fact, there is no direct LP algorithms because this convex region is a polytope which has exponentially many facets. Meaning if we try to express it as a linear program, we would need exponentially many constraints. But this still leaves open the possibility that you could potentially represent this polytope by a small linear program in a higher dimension. In particular, even it's often the case that in linear programs, if you include additional auxiliary variables into the program, you can reduce the number of constraints that you need. So to give a geometric example, so imagine this polytope P, which is the red region, is what we are trying to express. In order to express the red region, it's an octagon, so you'd need 8 constraints for every one, one constraint per side. But if you instead express this polytope as a projection of a 3-dimensional body, you can express it as a projection of that 3-dimensional body, which has just 6 facets. So now you can get a LP with 6 constraints that expresses the same region. And more generally for the traveling salesman problem, what we're looking at is a size R extended formulation for the TSP polytope is basically a polytope P in some dimension R, which is larger than the original dimension n squared, such that if you project onto the n squared coordinates, you get back the TSP polytope. Should have figured this out. Okay. Yeah. And in this talk, actually, we'll be interested not in linear programs, but in semidefinite programs. But the idea is here, again, the same. We are trying to express the TSP polytope as a projection of a higher dimensional semidefinite program, or a spectrahedron. The feasible region of a semidefinite program, we'll call it a spectrahedron. So pictorially, let's say this is our TSP polytope, and what we're trying to do is, we are asking the question, this polytope is complicated, but can we express it as a projection of a simple spectrahedron? Okay, and this is not something which is unusual to algorithms. In fact, it's quite often the case that one can express a fairly complicated polytope in a simple way using a projection. So one of the most common examples is the unit L1 ball. If you look at the unit L1 ball, this is a convex set, it is a polytope, which has, in general, it has 2 to the n facets. It's a 2 to the n linear inequalities, but if you include additional variables yi, then you can express this as a projection of a polytope in 2n dimensions with only 2n plus 1 linear inequalities. And it's not just this case. Many natural algorithms like spanning tree, the fact that minimum spanning tree look at the minimum spanning tree polytope, or the Held-Karp TSP linear program. Many natural algorithms fall into this class where you take a polytope which is potentially has exponentially many facets, but express it as a projection of something which is simpler. And if you look at the linear programming and semi-definite programming hierarchies, what they do is they give us a systematic way to do this process, to lift the given polytope to a higher dimension and obtain a relaxation for the polytope in the higher dimension. Okay. But we know that the TSP problem is NP hard. So in particular, we expect that even using extended formulations, it should be exponentially hard to solve the TSP problem. And so that's really the goal of this line of work, is to show that there are no small extended formulations for polytopes for NP hard problems or problems which we believe are hard. So this line of work started with the work of seminal work of Yannakakis in the late 80s, who showed that the TSP polytope does not admit any extended formulation smaller than 2 to the omega n, if I add a restriction that the formulation is symmetric. And this, the state of affairs stayed the same until about a few years ago, like 4 years ago. Fiorini et al. Showed that you can remove this symmetry restriction, and they showed that arbitrary extended formulations for the TSP polytope take exponential size. And in a prior work with Lee and Steurer and Tan, we had showed an exponential lower bound for symmetric SDPs for TSP polytope. And what I'll talk about today is how to get lower bounds for general semi-definite programs for a given polytope. Okay, that will be the. And the same results can be also applied to other polytopes like cut polytope, correlation polytope, or more generally for classes of problems. One way to think of this in terms of complexity theory is to think of it as a sort of an unconditional lower bound in a restricted model of computation. And this restricted model of computation captures solving linear programs, and spectral algorithms, because SDPs capture, in a sense, capture linear programs and spectral algorithms. Okay, so just to recall, let me start by recalling the Gomans-Williamson semi-definite program for max cut. So here's a problem. So you're given a graph, and what you want to do is to separate the vertices into 2 parts such that you maximize the number of crossing edges. Okay, that's the max cut problem. And here's a semi-definite program for max cut. The semi-definite program for max cut assigns to every vertex a unit vector, which is supposed to be 1 if it's on this side of the cut and -1 if it's on this side of the cut. And you maximize the total squared distance between these vectors. Clearly that measures the number of edges cut, and subject to the constraints that these are unit vectors. This is a very simple semi-definite program. But if you look at it closely, what's going on here is the feasible region for this, the set of all feasible solutions for this program, they look like the set of all positive semi-definite matrices, n by n positive semi-definite matrices, where the diagonal entries are 1. So in particular, the feasible region is independent of the graph. the feasible region does not depend on the graph. And what you're optimizing, this quadratic function, becomes a linear function in the entries of this matrix. So here's a format in which this SDP looks like. This SDP has a feasible region that depends only on the number of vertices and not on the graph. And the objective function, or the entire graph, is actually represented only in the objective function that you maximize. Okay? The graph is the edges of the graph are represented only in the edges in the objective function. Okay, is it clear? So, this is a very specific semi-definite program for max cut. So now we ask, what does a general semi-definite program for max cut look like? So a general semi-definite program for max cut, it looks like the following. You have some feasible region, the spectrahedron, okay, and the spectrahedron S is just, you take a PSD cone, the cone of all PSD matrices, and you intersect it with a linear affine space, and the region that you get in the intersection, that's your feasible region. Okay, so that's a general spectrahedron, and a general semi-definite program for max cut will maximize a linear function on a spectrahedron. And the size of the semi-definite program will be the dimension of the PSD cone, or essentially the number of variables, or square root of the number of variables in your semi-definite program. Okay, that's how we'll measure size. So if your semi-definite program on R cross R PSD matrices, it'll be R. Okay. So operationally, the way to think of this is, these are lower bounds in a model of semi-definite programs where I allow you to write a feasible region which doesn't depend on the graph. You're not allowed to look at the edges of the graph when you write down the constraints of the program. The objective function can depend on the graph, but not the constraints. But you're allowed to add any number of additional auxiliary variables into the program. And that's what an extended formulation allows you to do. Okay, okay, so now I think with this background, I'm ready to state our main result. Essentially what we prove is the following. We prove that you take any max CSP, like max cut, the degree D sum of squares relaxation achieves the best approximation among all SDP relaxations of roughly the same size. What I mean by roughly the same size is that for every integer D, if you look at the degree D sum of squares relaxation, it's of size n to the D. And we show that no SDP relaxation of size smaller than n to the D over 8 can achieve a better approximation. So there is within polynomial factors within a polynomial blow up in the size of the SDP, you cannot get anything better than using a degree D sum of squares SDP. Okay, and this is a very general result. And we already know that lower bounds for specific problems for this sum of squares hierarchy. For example, we know that if you look at the 3-SAT problem, we know that no constant rounds of the sum of squares hierarchy can solve 3-SAT better than a 7/8 plus a epsilon. So this immediately gives a lower bound for general STPs. You can translate lower bounds for sum of squares hierarchy to a lower bound for a general STP this way. Any questions up to this point?
So this is the lower bound for all STPs whose feasible region does not depend on the graph?
Yes. Okay. Exactly, yeah. Anything else? Okay, so so there's a fair bit of prior work on this problem and related work. So as I said, the work started with the work of Yanakakis in 1989, which showed a lower bound for symmetric LPs, and more recently for general LPs by Fiorini et al. And there was a breakthrough work by Rothwas on matchings. And I think one of the closely related earlier work on this is our work with Sion Chan, James, and David Steurer, where we showed the similar result for linear programs. A similar result is true for linear programs, where you replace sum of squares hierarchy by the Sharali-Adams hierarchy. Okay. There are a lot of terminology that I'm using which I'm without defining it. Unfortunately, defining all the terminology could take a lot of time. But we will not use many of the terminologies that I am going to define. And the plan for the rest of the talk is I want to give a glimpse of the entire proof. But of course, there are lots of moving pieces in the proof, and but the hope is that I can show some key ideas which might be of broader interest. Okay, so firstly, there's a completely different viewpoint on some LPs and SGPs, which has come up in the last few years, which is a proof complexity viewpoint. So here's what happens when you solve an LP. You suppose G is a graph. You're given a graph, and you solve the max cut problem on this graph. You have the max cut problem on this graph. What is the max cut problem? It is maximize over all possible cuts this quadratic polynomial on the graph. Okay, and when you write a linear programming relaxation for this, what it really does is actually certifies an upper bound for the value of this optimum. Okay, it actually returns an upper bound which is provably correct for the value of this. Now you could ask, how does this certificate look like? This certificate has a very specific form. So let me just look at the so-called D-round Sharali-Adams. Okay, what does a D-round Sharali-Adams linear program do? It proves to you an upper bound on the value of the max cut. How does it prove to you an upper bound on the value of the max cut? It actually takes this function, g of x, okay, and it writes alpha minus g of x for some alpha as a positive combination or a non-negative combination of functions, each of which is a non-negative junta. You know, think of this fi, for example, is just an and on a bunch of variables. Okay. Now suppose I give you an equation like this, which is true as functions. As a function, the left-hand side is equal to the right-hand side. It certifies that g of x, alpha minus g of x, is non-negative, because each of the functions fi is just an and of a bunch of variables. Okay, therefore it's non-negative, and we are taking a positive non-negative combination of that. So therefore, this is a non-negative function. Since the right-hand side is a non-negative function, it certifies that g of x is smaller than alpha, right? And so essentially, a D-round Sharali-Adams linear program, when you solve it, it looks for the best alpha for which there is such a proof, and it returns to you the proof. It returns to you the proof, these lambdas, such that this equality holds. Okay? So that's how a D-round Sharali-Adams certifies an upper bound. Okay, this is a very succinct description of a Sharali-Adams linear program. Now we could ask, what does a general linear program do? What a general linear program do is also something very close. A general linear program with R constraints, if you have R constraints in a linear program, it specifies a family of non-negative functions. Okay, the linear program corresponds to a family of non-negative functions, and given a graph, it tries to write alpha minus g of x as a non-negative combination of these functions. So if you pick the family of functions to be just functions that depend on d bits, all functions that depend on d bits, you get Sharali-Adams. If you allow yourself any family of R non-negative functions, you get a general linear program. Okay, this is actually just a reformulation of Yanakakis' framework for proving lower bounds, but it's very succinctly stated this way. So now let's look at semi-definite programs. Okay, what happens in semi-definite program? So in a semi-definite program, it returns a certificate of the following form. When you solve a degree D semi-definite program, it writes alpha minus g of x as sum of squares of degree d over 2 polynomials. Okay, here it's even, yes?
Is it like trivial? We need to see why every LP can be expressed in this?
No, actually, yeah. So I should say many of the things I'm saying are not easy to see, but They're not technically deep. They're not technically deep. They just, one needs to just work around the definitions of these objects and take the use duality. They're not very technically deep. Their proofs are probably half a page or something, but just So it's just a reformulation of the definitions. Okay, so here what does a degree D sum of squares program do? A Lasserre hierarchy. What it does is it takes alpha minus g of x and tries to write it as sum of squares of d over two polynomials. Now clearly the right hand side is always non-negative, which certifies an upper bound on the value of g of x. Okay, and now you can guess what a general SDP does. If you think about a general SDP of size R, the SDP is specified by a vector space of functions. There is a vector space of functions f1, let's say the span of f1 through fr. Okay, in the case of degree D sum of squares, the vector space was this vector space of all degree D over two polynomials. Okay, so what the certificate looks like is it writes alpha minus g of x as sum of squares of functions from this vector space. Okay. So that's what a general SDP does. So proving lower bounds for general SDPs corresponds to just the proving lower bounds against this model of proofs. You want to, where the SDP specifies a vector space of functions, and it tries to write every graph that you give as in this form. Okay, and if the vector space is low degree polynomials, it just gives you degree D sum of squares. Okay, yeah. So just to take this analogy a little bit further, so what does a hard instance for the sum of squares hierarchy look like? If you look at a hard instance, it's a graph such that somehow the sum of squares hierarchy fails on it, meaning this function alpha minus g of x for some value of alpha is not the sum of squares of degree D over two polynomials. Okay, that's what a hard instance, an integrality gap instance for a sum of squares hierarchy is just a graph for which this function cannot be expressed as sum of squares. So geometrically, what it looks like is, you have this cone of things that can be written as sum of squares of polynomials, and this function that you're trying to look at, alpha minus g of x, sits outside this cone. And whenever you have such a thing, by simple convex geometry, you have a half space that separates the cone from this point. Okay, we'll use this half space later, but let's call this half space something. Let's call it D. Okay, there's a half space such that every non-negative square function is every square of low degree polynomial is on one side, and this point that you care about is the hard instance is on the other side. And this D is such that D inner product, it's the half space, so D inner product f is greater than 0 on this side, D inner product f is less than 0 on this side, and D is, we call it the distinguisher. Okay, this is just duality, not. Okay, that's how a hard instance looks like. Okay, now here's, we'll go a bit further. A priori, this picture is actually in the space of all functions, right? The space of all functions, then you have the cone of things that are squares of low degree polynomials, and then you have alpha minus g of x, and you have a separator. A priori, D can be arbitrary degree, but actually D is low degree. Why is that? Because this picture can also be drawn not in the space of all functions, but in degree D polynomials, right? This picture is actually over degree D polynomials. You can think about it that way, because the functions that are sum of squares of degree D polynomials is degree D. So this is in degree D. This is in fact degree 2. Alpha minus g of x, if you recall, it was just alpha minus a quadratic function. It was a degree 2 polynomial. So you can assume that the distinguisher is a degree D polynomial. Okay. Alpha is the upper bound, so you can think of the integrality gap value, integrality gap ratio. Yes.
When you say D is a half space, you mean if the half space where the monomials are actually functions?
Yes, D itself is a function. D is a function. Yeah. D is a function, and then it's a half space in the space of functions, right? So it's in D in a product F is greater than 0 here, less than 0 here. Okay, so here's sort of what we're going to do, right? So we want to prove a lower bound against general SDPs for max cut. Okay, so what do we want to do? We want to construct a family of instances of max cut, like a bunch of graphs, such that whichever vector space of dimension R that you pick, there is one graph in the family which is not the sum of squares of functions from the vector space. Right? So our task is a little bit harder than usual because now we don't know the vector space V, but whichever vector space you pick, you should not be able to write one of the graphs as a sum of squares of functions. So I can describe how our family of graphs is going to look like. Our lower bound family of graphs is just the following. Pick a graph which is a hard instance for degree D sum of squares SDP, right? The Lasserre SDP. So this graph cannot be written as sum of squares of low degree polynomials. And let's say this graph is on k vertices, right? You can think of k as a constant, like 1,000 vertices. Okay? Our family of graphs will just be take an empty set of n vertices and just place this graph arbitrarily in all over this empty set of n vertices. Okay, so this gives you n choose k different graphs by just placing this everywhere. That's a family of graphs. And what we're going to show now is G itself was hard for low degree polynomials. This family of graphs is hard for every vector space. Okay, so that's what we want to show. We want to show that this family of graphs is actually hard for every vector space. Whichever vector space you pick, there's something here that you cannot write as a sum of squares of that. And so, okay, ignore all the text. So what's the what's the idea? Well, the natural idea would be to the following, right? Give me any vector space. I will try to approximate it by low degree polynomials. Since the graphs here cannot be written as squares of low degree polynomials, if you can approximate a vector space of functions by low degree polynomials, it should give us a lower bound, right? So our general strategy will be, given any vector space V, we want of some dimension R, we want to approximate it by low degree polynomials, such that this this thing goes through. Now, then the natural question is, how good should this approximation be? Okay, should we want epsilon error in what norm, and how do we want this? And so the answer is, the approximation only needs to be good to fool our distinguishers. Remember, we had these distinguishers, this green half space. Our approximation to the vector space only needs to be just as good to fool these distinguishers. Okay, so here's our task now. So we are given some vector space of functions. So these are functions on the hypercube. We are talking about functions on the hypercube. We're given a functions on vector space of functions on the hypercube. What we want to do is to approximate the entire vector space, in particular every function in the vector space, by low degree squares, okay, low degree polynomials, such that if you look at a distinguisher, if you apply the distinguisher function di to f squared, it should be the same as applying di to your approximation. Meaning the distinguishers di cannot tell whether you're giving it f or q. Okay, so even now this problem seems unusually hard to solve because I haven't said anything about the vector space V. So a priori it's not clear that there will be any such low degree approximation. What if V consists of only high degree polynomials? How can you approximate by low degree polynomials? Here there's actually a very nice meta observation, which is not which is not new to us. It was new to me when we did this work, but it's definitely not new in complexity theory. It repeatedly shows up. Here's the meta observation. Suppose you have an object, and you're trying to approximate this object with respect to some set of tests. Now, what is the complexity of the approximator that you produce? A priori, you'd expect that it basically depends on how complicated the object is. But actually, many cases or most cases, it actually only depends on the complexity of the tests that you're doing. This is actually fairly it repeatedly shows up all over complexity theory and even in additive combinatorics and so on. Just that if you're trying to approximate an object, the complexity of the approximator doesn't depend on the object, but more on the tests. And this is actually fairly obvious in some cases. Suppose I give you a function, and I ask you to output an approximator such that it fools inner products with low degree polynomials, degree D polynomials. The natural approximation is you take your function, you just project it onto the degree D space, because now the inner products with every degree D polynomial is preserved, and the approximator is degree D, right? If you just had to preserve, if you give you a function and you want to preserve degree D inner products, you just project it onto the degree D polynomial space, vector space spanned by that, and you'll preserve all the degree D inner products. So this meta thing, it plays a crucial role here. In particular here, you would intuitively expect, because of this, that although the vector space could be arbitrarily complicated, since we know a lot of things about the functions di, right? In particular, if you recall, we knew that the di's are low degree. Since the tests that you're making are low degree, you can hope that the approximator is also low degree. Yeah?
Can you repeat again why the tests are low degree?
Why the tests are low degree? Well, the only thing we wanted from this test is that it separates the cone of low degree squares from this point alpha minus g. This is a quadratic polynomial, and this is a low degree squares. So therefore, you can assume the separating thing is also low degree. Okay. Okay. So basically, we prove an approximation lemma. Which I'm going to state it, but you don't have to remember all the parameters. But just for completeness, I'm going to state it. So suppose I give you any vector space of functions v, and I give you a family of tests, like a family of low degree tests di. Okay, you can take any function in V, in the vector space V. You can approximate it by a sum of squares of polynomials of degree something like d times, these parameters are there, d times b times log r, but low degree, such that if you apply the tests on f squared, it's same as applying the test on some of these squares of these this approximator up to an additive plus or minus epsilon error. Okay. So that's the main approximation lemma, and once you have this, the proof is somewhat easy, or okay, let's see how the proof goes once you have this. Suppose you have this approximation. I've just said that every vector space you can approximate by sum of squares of low degree polynomials. Okay. So this is very good, except for one issue. The sum of squares of low degree polynomials that you got has degree more than d, much more than d. Okay. Our distinguisher could only work on degree d things. Right, if a distinguisher was degree d, could separate degree d from the distinguisher d could separate this from the square of degree d polynomials, but the approximator that we got is much higher degree than d. This is to be expected because we're trying to fool a set of tests. So the thing that fools these tests will be much more complicated than the test. I mean, at least a bit more complicated than the test. You'd expect that it's maybe degree 2d, it's actually slightly more than d. So it seems like we are stuck because, we wanted to fool the tests, but we got an approximator that's way more complicated than we hoped for. It's much more degree than d. But here, there's a very standard trick in complexity theory which comes to a rescue, which is a random restriction. If you so what is random restriction? In our case, is the following, right? So we had, if you recall, we had n vertices, and we placed our graph at on the hard instance somewhere randomly among these n vertices, or on every subset of size k. So let's think this through. Suppose you have a polynomial p which is of degree n to the 0.1, a pretty high degree polynomial, but not entire degree n, but degree n to the 0.1. It's a fairly high degree. Okay, but now what we did was we took an empty graph and we placed our hard instance on a subset S, right, somewhere. That's what our family of graphs was like that. You took an empty graph and placed a hard instance all over the place. So our family of graphs actually is built for random restriction. It's built for ensuring that most of the vertices of the graph don't matter. All the action is happening in a small subset of the vertices. So in particular, if you have a vector space that's approximated by some polynomial of degree n to the 0.1, when you restrict your attention to a random subset of vertices, this polynomial is going to look like it's low degree. You take any polynomial whose degree n to the 0.1 and look at a subset of size even n to the 0.1, or even something smaller, log n, let's say. Restricted to this, the polynomial will look very low degree. And the idea is very simple, right? So look at any monomial, right? Look at it's a polynomial. Look at any term. Yeah.
How many copies of Jupyter?
One copy, just one. So yeah, everything else is empty. So it's a family of graphs where most of the graph is empty and you have one copy of the hard instance somewhere. Okay? So every other vertex doesn't matter. Okay, so now we look at any so you have talking about polynomials, let's just look at any monomial. You have product of phi and t xi, so it's a monomial. Let's see what happens to this monomial when you restrict to a random subset. Okay, so this is the monomial, and it's a very small monomial in the sense that it's degree at most n to the 0.1. Now you pick a random subset, and what do you expect? In fact, most of the time this subset doesn't even intersect this monomial, right? So this monomial becomes trivial most of the time. When is it degree 1? When the subset that you pick and the degree, this monomial intersect at one vertex. That happens with probability 1 over n or something rough like that, right? And if you intersect two vertices, 1 over n squared. In fact, the probability that the intersection between s and t is d over 2 should be roughly n to the minus d. So therefore, it grows. So even if you have a degree n to the 0.1 polynomial, its restriction will look very much like low degree. And this is what helps us to do the random restriction. Okay, so okay, I'm just going to show the piece which I left out is how do you construct this approximation. And in fact, that's sort of the most interesting piece of this puzzle. I'm going to sort of show you how it's done. So, let's forget whatever happened in the talk before. Let's just concentrate on this problem. Okay, it's a one-dimensional problem. I just given you a probability distribution f on 0, 1 to the n. It's a probability density f. Okay, this is the object that you want to approximate. Okay, it's a probability density. And you have a set of test functions, d1 through dm, that you want to fool. Okay, these are the tests that you want to fool, and this is a function that you want to approximate. So this is what we'll prove now. We'll prove that there exists an approximator for this, f, phi. Phi is an approximator. So phi is also a probability distribution. Phi fools every one of the tests, meaning for every one of the tests, if I look at di in a product f, it's within plus or minus epsilon of di in a product phi. And of course, the most important thing is we want phi to be simple. Here f was arbitrary. Basically, f was an arbitrary probability distribution. What we want is phi to be not simple. In particular, we want it to be not much more complicated than the tests. Okay. So how do we do this? So the main technique here is multiplicative weights. Okay, so I'll show you what is going on. So in this thing. So here's what was given. You have a probability density and you have a set of tests, and you want to construct an approximator. So here's a simple multiplicative weights or mirror descent algorithm. So you start with, okay, I think my picture shows up at the end, sorry. Yeah, so you start with the most basic guess. So, okay, so let me explain the picture. You have a simplex, you have the set of all probability distributions on 0, 1 to the n. Okay, this is the simplex. The function f that you're trying to approximate lives somewhere here. Okay, you start with the simplest possible hypothesis or simplest approximator, which is the uniform distribution. Just the function phi naught is equal to 1. The uniform distribution, the constant function, is your initial guess. Okay, but of course this will not satisfy one of the tests. There will be a test such that the di inner product f will be off from di inner product phi by more than epsilon. There will be a more than epsilon error. So then you do a multiplicative weight update. So a multiplicative update is you multiply phi by essentially e to the di of x. This eta is the step size here. It's usually need in gradient descent or mirror descent. So you do a multiplicative weight update, you get a new point, phi 1. Right? And then you repeat this every time you look for a test that is failed by your current approximator, and you do a multiplicative weight. Okay? And by a fairly standard analysis of multiplicative weights, you can show that at each step, the KL divergence between your current point and f decreases. You get closer and closer to f at each step. It decreases, the KL divergence between the current point and f decreases. And which means that this will terminate pretty quickly. Pretty quickly you will reach a point where you will have a function that satisfies all the tests. Okay? And because you constructed using this, constructed this function via this algorithm, meaning you, each time you have a very specific form for this. Here z is just a normalization. You want to stay in the space of distribution, so you normalize whenever you multiply. But because you constructed the distribution algorithmically, constructively, you know very specific things about this distribution. In particular, you know exactly how the thing looks like, right? You know that phi of x eventually will be e to the power minus epsilon or in eta times summation di. Right? That's the form of this expression. Right? It will stop after t steps where t is some constant, but t is some function. So, you know, already this says that if your di's are simple, this function is somewhat simple. Right? So if your distinguishers, for example, if every distinguisher was a d junta, it depended on d coordinates. Now then phi depends on d times t coordinates. If your distinguishers are d juntas, then this is a d times t junta. So this is actually good enough to show many LP, all the LP lower bounds for Chevalier, you know, that I stated earlier. Okay? So, but if you recall, our goal was to approximate the function by sum of squares of low degree polynomials. Right? So therefore, how do we get that? It's also very simple once you have this. Well, you know, if you look at e to the power epsilon summation di, you can write it as e to the power epsilon summation di over 2 whole square. Right? That's just math, I guess. And then you expand the exponential function by Taylor series, and you can truncate at a point. And now you have phi as a square of a function, square of a low degree polynomial. Okay. Okay. So that's basically what is going on. That's basically how we get an approximator. But the one complication which we didn't see is here we are approximating a single probability distribution f, but actually we wanted to approximate an entire vector space of functions simultaneously, right? But that complication only means that instead of multiplicative weights, you need to use matrix multiplicative weights. Okay, you just need to use matrix multiplicative weights, and instead of multiplicative weights, and the analysis is essentially the same. Okay, so I think I'll stop pretty soon. So the open questions here is the results that I stated only hold for relaxations of size up to n to the log n. Okay, and the question would be, can we extend this optimality of Shirley-Adams or Lasserre SGPs beyond relaxations of size n to the log n, meaning up more than log n rounds, As of now, we only know this for up to log n rounds. In recent work with Kothari and Raghumeka, we showed that we can do this for linear programs, meaning for linear programs of almost sub-exponential size, the Shirley-Adams LP is optimal. It would be interesting to do this for semi-definite programs. I think I'll stop here. Yeah.
This is a question about the improvement. Like, you can answer later. So is it a better embedding or a better approximation in terms of to get the into the 0.0? It's a different random distribution.
It's a different distribution on the instant on the underlying distribution is different. Yeah, on that. Yeah.
Yeah, I can ask you more.
Yeah.
Just one more question. So how general do you think this paradigm of going from summer squares lower bounds to extended formulation lower bounds is? Like, for instance, do you think it can apply to not just max CSPs, but maybe some minimization problems or the other maximization problems where the optimal solution answer is not a constant fraction of all the constraints?
Potentially, I don't know. Yeah, potentially it could. Yeah, I don't have a definitive answer. Yeah, it's very likely.
So is there no more questions?